The paper we're diving into today is On Einstein-Minkowski-Osiak Relativity by David Lush.
Okay, that's quite a title, right? I feel like just saying it out loud almost makes me smarter. But yeah, so this paper by David Lush is basically revisiting, well, challenging actually, some of the key ideas we all thought were settled in relativity.
The core question is, honestly, a wild one. What if the textbook version of Einstein's relativity isn't the only game in town? Lush explores an alternative called Osiak relativity that's based on different mathematical assumptions. Specifically, it argues that if you base your descriptions of particle mechanics on fully Lorentz-invariant Minkowski equations, so four-dimensional equations, rather than the usual three-dimensional Planck ones, you actually get different formulas for energy.
And it's not just some subtle difference. It literally changes what the rest energy, kinetic energy, and total energy of a particle are supposed to be. Apparently, in this Osiak version, the rest energy is E0 equals mc squared by 2, instead of the classic E0 equals mc squared.
Yeah, which, if you love your Einstein posters and mugs, kind of hurts, right? I mean, E equals mc squared is like the most famous equation in physics.
I know, but the significant thing here is Osiak relativity doesn't conserve energy in relativistic collisions the way Einstein's version does. Instead, it preserves something called the temporal component of 4 momentum. So, for all practical purposes, like the energy thresholds that smash particles together, they still come out right, but the underlying principle isn't energy conservation, it's temporal momentum conservation.
That is a lot to wrap your head around. I love that nerdy distinction, though. It's a reminder that the universe doesn't care about what's in our textbooks. But back up. Does this mean all the observed conservation laws are just aspects of momentum conservation in this framework?
Pretty much, yeah. If Osiak relativity accurately describes nature, then what we've been observing and calling energy conservation is actually a reflection of 4 momentum conservation. Which, honestly, makes me a little dizzy, but...
No, same. Because that's like saying all of these collision experiments we've done, all of physics built on those, maybe our explanation's been wrong, even if our calculations lined up. It's very, you've been using the right recipe, but you don't understand why it works.
Exactly. And Lush really stresses that this isn't just theory for theory's sake. Like, he mentions possible consequences for dark energy and dark matter. That if energy isn't strictly conserved, maybe that missing energy we attribute to dark energy or dark matter is just, the universe not keeping the kind of books we expected.
I mean, it would be kind of poetic if dark energy was just the universe bungling its accounting.
Or being way more clever than our equations. Oh, also, this is a fun side note, and then I promise we'll get back on track. Lush goes off about how, under Osiak relativity, the electromagnetic field should be complex-valued, not just real, which could maybe connect to why quantum mechanics uses complex numbers everywhere.
Yeah, that's wild. Like, maybe the math weirdness in quantum stuff isn't just quantum is spooky. Maybe it's just our relativity being incomplete.
And to make it even more spicy, Osiak relativity resolves some persistent puzzles, like the spin-orbit coupling anomaly in atomic physics. In this new framework, the energy levels just make sense without introducing things like Thomas precession, which always felt kind of like a fudge to me.
This brings up a meta point, actually. One thing I keep coming back to, reading through this paper, is how scientific theories aren't absolute truths. They're frameworks. And sometimes we find out the framework we've been using is kind of off. But if it still made good predictions, should we care? Or should we push for something more fundamental, whatever that means?
Yeah. Like, does it matter if it's momentum or energy being conserved, as long as a collider produces the right amount of stuff? Maybe it only matters when we want to explain something that doesn't fit, like dark energy.
And honestly, listeners, that's the kind of philosophical rabbit hole academic research leads us down. Lush isn't claiming he's found the truth, but he's showing that there's more to explore. And sometimes that means turning long-cherished ideas on their heads.
If anything, it's a good reminder not to take textbook physics as unchanging gospel. The real universe might still have surprises up its sleeve, just waiting for someone to reconsider what everyone else took for granted.
Absolutely. The paper we're diving into today is The Magnetic Force as a Kinematical Consequence of the Thomas Precession by David C. Lush. Quite a mouthful, right?
Yeah, I had to read that title a couple times before it started making sense to me. But it's actually asking a really big question. Could the magnetic force, like the same kind of force we see in everyday magnets, just be a kind of side effect from the weird way space and time behave when things move really fast? Especially when you bring in something called the Thomas precession.
Exactly. And just for anyone who maybe hasn't thought about Thomas precession since physics class, or, ever, it's this rotational effect you get when a particle moves and accelerates at relativistic speeds, meaning near the speed of light. Basically, it makes the reference frames of moving particles rotate relative to each other.
And that's super fundamental. Lush's core argument is, what if the magnetic force, instead of being just one piece of Maxwell's equations, a kind of force on its own, is what you'd expect to pop up just from this kinematic twisting, this Thomas precession, as you switch reference frames?
Right. The significance here, and why I think it's actually pretty bold, is that it tries to demystify magnetism even further. Instead of electric and magnetic fields are two sides of the same coin, which is standard relativity, it goes, hey, maybe the magnetic force is what you have to see if you're tracking with all the correct frame rotations as charges get pushed around. It's like he's saying magnetism isn't its own thing. It's just the price of doing kinematics correctly in relativity.
Uh-huh. So to unpack the main method a bit, Lush considers two classical charged particles, one acting as a source and not accelerating, like it's super heavy or maybe it's part of a wire so it can't move. The other's getting flung around by the electric field, the Coulomb force. He's walking through like, what does the observer who rides along with this test particle see? From her perspective, reference frames are precessing, twisting around, all because of the Thomas effect.
And what's wild is that when you tally up all the pseudo-forces she expects, Coriolis, centrifugal, Euler, like the kinds you get on a spinning merry-go-round, some are there, some aren't. Specifically, there's no Coriolis force in the source particle's rest frame, because from that particle's point of view, nothing's turning. This means, though, that an anti-Coriolis force has to be popping up somewhere, almost as compensation. And that's what, in the usual inertial frame, looks exactly like the magnetic force. Seriously, that connection feels so satisfying. Like, you almost want to high-five relativity.
I know! And it's not just a formal analogy. In his equations, the magnetic force in the lab frame is identical to this missing or anti-Coriolis force viewed from that precessing test particle frame. You can see the math. He even gets the mass dependence to drop out, just like the real magnetic force, which only cares about the velocity and the charges.
And, he doesn't stop there. He teases out, okay, if the Coriolis term gives you magnetism, what about centrifugal and Euler terms? Could they hint at the origins of the strong and weak nuclear forces? I mean, that's a hefty leap, but his argument is that at really high energies, like inside an atomic nucleus, there might be a Thomas precession-induced anti-centrifugal force that could be, well, strong and always attractive. He goes as far as to do some quick calculations, comparing how it might stack up to the size of a nucleon. Spoiler, it's a bit too weak, but not wildly off.
He does admit that this isn't the last word, like it's just a start. There are things he hasn't calculated, like the effects of field retardation, so it's not perfect. But, the idea that maybe the deep forces of nature and all the fields we've cooked up, to Lush, maybe they're just labels we slap on the weirdness of special relativity plus classical kinematics when you're really strict about it.
There's something almost philosophical there, right? Like, is a force always a force? Or sometimes just the universe's way of bookkeeping as things zoom around with Einstein's rules?
For sure. And sometimes I wonder, like, if you could go back and tell Faraday or Maxwell, hey, what you thought was a core force of nature might just be a perspective effect if you're riding along with the particles, would they be delighted or horrified?
Ha! The paper we're diving into today is Dark Matter as the Difference of Inertial and Gravitational Mass by David Lush.
Yeah, and wow, what a title, right? Dark matter as the difference of inertial and gravitational mass. It already hints this isn't your usual let's find a weird new particle approach.
Right. So the core problem Lush is addressing is the whole dark matter mystery. You know, galaxies spin way too fast to be held together by just the visible stuff: stars, gas, dust. For decades, we've wondered, what's this invisible, dark matter giving them their extra gravitational glue?
But here, Lush comes at it from a totally different angle. Instead of inventing new matter, he's basically saying, well, maybe the laws we use to add up mass, inertial versus gravitational mass, need a rethink. That's pretty wild, because, in physics class, weren't we taught those two are always equal?
Exactly, and that's key. So he's questioning something fundamental. Lush builds his argument by combining two unconventional theories. One is Osiak's tweak on special relativity, and the other is the Harari-Shoup model, which says that even the building blocks of matter, quarks and leptons, are made of even tinier things called preons.
Yeah, that preon thing is wild. In the Harari-Shoup model, every elementary particle is basically a combo of just a few types of preons and antipreons. So, at that level, matter and antimatter are thoroughly mixed together, which is not what we usually think.
Right. So, if you take that and then bring in Osiak's alternative relativity, which, among other things, apparently allows different ways of adding up energy and mass for composite systems, suddenly you can get situations where a lump of matter's gravitational mass, the amount it pulls gravitationally, is different from its inertial mass, the amount it resists being pushed.
Okay, so you're saying that in this hybrid theory, a hunk of matter might weigh more gravitationally than it weighs when you shake it or put it on a scale?
Exactly. And that might sound bizarre, but Lush argues that we only measure mass via inertia, or the weight in the local gravitational field. But if these quantities diverge because of this preon-antipreon mix, we could be underestimating the true gravitational mass of, say, a whole galaxy.
So under this model, when astronomers measure the mass of galaxies using stars' orbits, the numbers seem too low. But that's because they've been using the wrong version of mass all along?
That's the idea. If we've been equating inertial and gravitational mass, but in reality gravitational mass is higher, then the so-called missing mass, the dark matter, is just this difference. It's not made of exotic new particles, it's baked into the fabric of what we already have.
One thing that fascinated me was that Lush even tries to estimate the ratio of dark to visible matter by tallying up preons and antipreons in a typical atom, like deuterium, and he ends up getting numbers that aren't far off the dark to visible matter ratios we see in observations, like 6:1.
It's definitely a hand-wavy calculation. He even admits that. But the fact that it lands in the same ballpark is, at the very least, pretty suggestive. But of course, these models aren't mainstream.
No, but it kind of gives you a different feel for what academic research means, right? Like, it's not that he's claiming absolute truth, it's more, here's a framework, here's a way to see familiar problems from a new angle, and if it sparks an experiment or a new analysis, then awesome.
True. And he does mention possible ways to test it. Like, if you could somehow make highly precise gravitational constant measurements with test masses of radically different composition, you might see tiny differences. That would give a clue.
That reminds me of, sort of like the early days of atomic models, when you know you're missing something, but you're not sure where the fudge factor is yet.
Or like when people first suggested the neutrino to explain missing energy in beta decay. At the time, maybe it seemed desperate. Now it's basic knowledge.
You know, I think I read somewhere that most dark matter searches have been looking for new particles, and, well, nothing so far. This paper offers a reality check. Maybe we're barking up the wrong tree?
Or at least, maybe we shouldn't rule out wild alternatives. The paper we're diving into today is Dirac Quantum Theory Using Alternative Relativity by David Lush. It's quite a dense read, but wow, there's a lot in there to unpack.
Yeah, I have to admit, when I first saw that title, I thought, here we go. Someone's ruffling the feathers of physics again. But, it's actually addressing something pretty fundamental. How we reconcile quantum theory, especially the Dirac equation for electrons, with an alternative form of relativity, not the one we're all used to from Einstein.
Yeah, exactly. The core question Lush is digging into is, what does it mean for quantum theory, particularly Dirac's framework, if we adopt Osiak's alternative relativity, rather than sticking to textbook Einsteinian special relativity?
And right there, that's a big deal, because Einstein's relativity underpins so much of both classical and quantum physics. But Osiak's version gets kinetic energy from integrating the Minkowski equation of motion, so a fundamentally four-dimensional Lorentz invariant equation, instead of the usual Planck force equation that's only three-dimensional. That sounds subtle, but it totally shifts how energy is calculated.
The headline is that, according to Osiak relativity, the energy of a free particle is halved. Like, for a resting particle, its famous E equals mc squared energy becomes just mc squared over tav. Lush shows this doesn't break Dirac's theory for a free electron. In fact, it sheds new light on things like antimatter and the way matter and antimatter pairs get created and annihilated.
I liked that discussion about negative energy states in Dirac's theory, too. Traditionally, those negative energies get interpreted as antiparticles, like positrons, traveling backward in time. That's wild enough, but in Osiak's setup, those states have positive energy, but the temporal part of their form momentum is negative instead.
That's such a twist, right? We usually equate the temporal part of form momentum with energy. Osiak says, no, they're separate. The temporal form momentum stays the same as in Einstein's version, so the rules for things like particle creation thresholds still work. But what we actually call energy just isn't the same thing anymore.
And, honestly, that brings up sticky questions for conservation laws, which we've always considered almost sacred. In Osiak relativity, energy can be non-conserved, especially in highly relativistic collisions. But form momentum is still always conserved. It might sound like theoretical hair-splitting, but Lush argues that this could actually help explain puzzling phenomena like dark energy or even cosmic inflation.
It sort of flips the script. People worry about energy non-conservation, but maybe, in some extreme conditions, that's the missing ingredient we need. There's even a proposal that the so-called missing energy fuels universal expansion.
And there's this bit about photon energy, which sort of, tripped me up for a second. In Osiak's setup, a photon's energy is h nu over 2 instead of h nu. And that fits better with some old arguments about the standing waves in the blackbody radiation problem.
The way he links that to de Broglie waves is clever too. If you have the rest energy but use the electron's spin, since electrons have half the spin of a photon, you end up preserving relationships between frequency, energy, and momentum. It keeps the mathematics of Dirac's theory intact, but the interpretation is kind of, well, you have to change your mindset about what's real.
And if you're listening, you might be asking, does any of this matter, or is it just mathematical games? Lush argues there could be experimental tests, like in pair creation events. He claims that if you could watch carefully enough, Osiak's relativity predicts the positron, the antimatter electron, should be detectable before the pair event, annihilating before it's even created. It almost feels like a physics prank, but that's what his equations say.
Right, so in principle, The difference between Osiak's and Einstein's relativity could be tested, at least if our particle detectors get fast and precise enough. You know, sometimes I wonder if, in 100 years, people will look back and see debates like this as the real groundwork for how we explain dark matter and dark energy.
I doubt I'll be around to see it, but yeah, maybe. Of course, the idea that all these conservation laws, like energy, are only true under some definitions is a little unsettling. Reminds me of when we learned that, Pluto wasn't a planet anymore. The definitions change, but the physics, well, the phenomena, are still there regardless.
That's such a great analogy. Science keeps evolving, and sometimes what we take as foundational is just the best story for now. The paper we're diving into today is Quantum Wave Mechanics as the Magnetic Interaction of Dirac Part by David C. Lush. It's a mouthful, I know, but stick with us. This one's actually trying to answer one of the deepest questions in physics. How is quantum mechanics connected to classical physics, specifically through the magnetic interactions of spinning particles like electrons?
Yeah, so the central problem here is all about the quantum wave function, right? That mysterious thing in quantum mechanics that tells us where particles might be. Lush asks, could this wave function actually emerge from just classical, relativistic electromagnetic interactions between particles if you model them with internal circulatory motion, the so-called Zitterbewegung or Zitter model?
Right. So instead of the wave function being this mysterious, standalone thing, he's looking at whether you can get something that looks and acts like the Schrödinger wave function, pretty much the core object in quantum mechanics, just from considering electrons as tiny charges spinning really fast at nearly the speed of light.
It's worth pausing on why that's a big deal. If you could show that all that weird quantum behavior, like particles being in two places at once or quantum tunneling, if that just pops out of good old classical physics with a tweak, it would change the way we think about reality. It doesn't solve everything, but it maybe demystifies a lot of quantum theory.
Exactly. So what Lush does is he looks at the force between two of these Zitter particles. Think of electrons as tiny spinning tops, but moving so fast they're practically at light speed. When you include the magnetic interaction between them and make things time-symmetric, meaning you include advanced and retarded electromagnetic interactions, a bit like Wheeler-Feynman's absorber theory, a new pattern emerges.
The core finding here is really cool. The magnetic force between these two spinning charges is modulated, meaning it oscillates, in a way that's mathematically very similar to the quantum mechanical wave function. It solves an equation that's almost the same as the Schrödinger equation, although in the standard relativity, it's almost because of a factor of 2 difference.
But here's where it gets twisty. Lush introduces a modified version of relativity from Osiak, where the relationship between mass and energy is E equals mc squared over 2, not the usual mc squared. When you use that, the modulation matches the Schrödinger equation exactly, with no extra factors.
I mean, that's pretty wild. If this alternate relativity is correct, which is, a big if, then quantum mechanics, or at least its central wave equation, might actually just be a feature of classical physics with this Zitter model. And to be fair, that's far from universally accepted, but it's an interesting proposal.
And let's not forget, he brings in the Wheeler-Feynman absorber theory to help explain how particles can have time-symmetric interactions. It's a bit mind-bending. Advanced waves, retarded waves, the idea that absorbers in the future and past play a role in what happens now. Sometimes it almost sounds like science fiction, but it's tied to real equations.
Absolutely. The upshot is that, under this framework, the wave function isn't some mystical cloud, but a manifestation of synchronized, or sometimes desynchronized, internal motions of spinning particles, communicating with each other via classical electromagnetic forces. It recasts quantum probabilities in terms of these phase differences between spinning particles.
There's nuance, of course. For example, Lush points out this only seems to work perfectly for particles with aligned spins and equal mass, which doesn't always fit the messy reality of protons, electrons, and composite particles. He speculates about deeper structures, preons inside electrons and quarks, which, honestly, is a whole other rabbit hole.
Yeah, and he admits there are still open questions, like how this framework handles cases where spins aren't aligned or particles don't have equal mass. He suggests that some modifications, like those preon models or more complex absorber behavior, might fill the gaps. But it's very much work in progress.
In the end, the real takeaway is that quantum mechanics might not be as mysterious or as fundamentally other as we sometimes think. Academic research like this doesn't settle things, but it gives us fresh ways to connect ideas and see where classical and quantum blur.
Exactly. Whether or not Osiak's relativity is right, or if every electron is really a bundle of jittery charges, the beauty here is that science keeps digging deeper, asking, could we make sense of the universe with the tools we already have, if only we look at them differently?
The paper we're diving into today is called Spin-Spin Interaction as Quantum Phase Measurement and the Mechanism of Atom Formation by David Lush.
Yeah, that's quite a title. And honestly, I feel like just the first line sets the scene for this incredibly deep re-examination of some basics from both quantum mechanics and classical electrodynamics.
Exactly. I mean, Lush is really trying to poke at what is at the heart of atomic formation. He brings up this idea that maybe we haven't really appreciated just how strong magnetic or spin-spin interactions could be under certain circumstances. Especially if, as the Dirac theory suggests, the electron always moves at the speed of light in these internal Zitterbewegung patterns.
Right, and let's maybe take a second on that. The Zitterbewegung thing, if you're not familiar, that's this idea from quantum theory that electrons aren't just sitting still when you think of them as being stationary. Instead, they're doing this wild, jittery dance at enormous frequency. The Dirac equation predicts it, but usually we treat it as a mathematical quirk, not a real motion.
Yeah, and Lush is saying, what if that's not just a quirk, but it's something you can actually use to explain how atoms come together? He posits that these high-speed circular charge motions, when you consider their intrinsic magnetic moments, could lead to spin-spin interactions that are strong enough to rival the standard electric, or Coulomb, force between charges.
That leads to the core question in the paper, right? Which is, could these spin-spin magnetic interactions actually be the real driver behind atomic formation, instead of the classic view where it's just electric attraction holding everything together?
And that question matters because, if it's true, then our entire fundamental picture of what holds atoms together would shift, from seeing the Coulomb force as everything to acknowledging that a hidden, really strong, spin-driven force is playing a bigger role.
One thing that caught me is how Lush argues that this interaction doesn't always appear. It actually depends on having particles with equal mass and spins that are aligned. So, like, two electrons with the same spin orientation could attract magnetically with a force similar in strength to the regular electric force, but if their spins are anti-aligned, this force averages out.
It's very selective, this coupling. And of course, that fits, in a weird way, with quantum statistics and why some atomic configurations are stable and some aren't. But Lush doesn't stop there. He speculates that quarks and leptons, so the really fundamental building blocks, might themselves be made from more fundamental spin half particles. Which, to be honest, is kinda wild, since it revives these ideas about substructure inside elementary particles.
I think that's what's kind of both exciting and daunting about this paper. It's not just proposing a tweak, it's basically saying, hey, you know the electron? What if that's not fundamental? What if it's made of three even tinier things, with their own spins and internal dances?
Yeah, and even photons might have structure, as Lush brings in. That, by the way, is something de Broglie and others mused on decades ago, but never really became standard.
So, in terms of method, much of what Lush does is take the classical electrodynamics we know and push it into this high-speed, almost always at light speed regime, and then calculates what the electromagnetic fields would do if these zitter motions were